Hold on one second.
Okay. Hold on here, I gotta get my notes.
Okay.
Okay, go ahead.
Good afternoon. Welcome to Purdue University for another session of the CERIAS Security Seminar. If you are viewing this live or sometime freshly after it was recorded in March of 2015, please take some time and visit the CERIAS website, register, get some information for the CERIAS Security Symposium coming up in a few weeks. So our guest today is from MITRE Corporation, a proud sponsor and partner with CERIAS. And our visitor is Dr. Andy Pyles. Andy is a senior cybersecurity researcher. Andy, welcome.
Thank you. So the actual talk today is going to be called, is part of the research I've been leading over the last year and a half over at MITRE. It's called VAMDA, or Virtual Android Malware Detection and Analysis. And so let's go ahead and get started here. So the problem that we're trying to really address here is more generally the app vetting problem. So the app vetting problem in general is basically trying to figure out, you know, if you've got an application, a mobile application, how do you actually vet it, or you know, how do you verify that there's no malware on there? So just to kind of set up this problem a little bit, there's basically, you've got the Google Play store that has over 1 million applications. Actually, I think it's like 1.2 million right now. There's also the Apple store, which has over 1 million applications. Then you also have like the third-party applications as well, like the Amazon, and a couple other ones like that. So all of those app stores really have this problem of like, how do you, if you've got this huge quantity of applications, like over 1 million, how do you process these things very quickly? So really what you want to look at is, the actual assurance level. So is this, if we're looking at a very low assurance level, then it's probably okay to actually take this application, vet it fairly quickly, and throw it on the app market so you can download it and so forth. However, if the assurance level is a little bit higher, then you may need to spend more time on that. So the way I look at that is there's basically the environment where, like, there's Google Play, there's a third-party app stores, but then there's the enterprise app markets out there, and these are basically enterprise or government entities where they've got where the actual assurance level is very high. They want to verify which applications are actually going on there. So that being said, so what we really want to understand for more of the advanced malware analysis problem is we want to understand, what is this app actually doing? Now again, at the Googles and Apples of the world, they're obviously concerned about this as well, but not at the same level as a government entity or enterprise. And so so in both cases, it's a very significant investment in time. You got to spend a lot of time on this stuff. The other thing that we want to look at is, okay, so then if you start looking at sophisticated malware may actually be hidden within the applications. And so some challenges with that is, in some cases, malicious payloads can actually be dynamically downloaded. So just by doing static analysis by itself, you may not actually capture this. So the other challenge is, what actually triggers malware? So we want to figure out, like, okay, is there some sort of external event? For example, there's a talk from 2012 by this hacker by the name of Charlie Miller. And he did a talk where he basically figured out a way of getting this, I wouldn't call it malware, but he got this application to actually run within the App Store that was not supposed to be run, and he actually got it through. He got his account banned, apparently, but so he actually did that. But what that shows is that the existing app vetting environments are not really suitable for some of this advanced malware that we're seeing out there. So the objective of VAMDA is to basically provide a platform for mobile malware analysis and app vetting. So we want to look at both the general use case and more of the advanced use case as well. And so it really, the idea is to reduce costs by automating certain manual work. So one of the things with enterprise where there is a lot of manual app vetting involved, there's a lot of labor. It can be very expensive because you have these specialists that are really looking through these applications one at a time, which obviously doesn't scale if you got millions of applications. So the other objective here is to design the platform for scalability. We want to be able to handle, if we want to scale up, handle multiple applications. We want to have that ability. So we've got this multi-tier architecture, which I'm going to explain a little bit later. We also want to accurately log, observe, and analyze mobile application behavior. And we want to, so the goal is to really record all relevant interactions. We want to record all that information. And finally, we actually want to provide the raw logs for further analysis. So some of the challenges here, as I've kind of mentioned some of these, but how do you trigger malicious behavior? So in that case, with the example I just gave with that, it's called the bouncer paper. I had the reference here somewhere. I'll tell you guys later. But if you look at that paper, it's basically what they did is they just checked to see, okay, I'm running within a virtualized environment. I'm not going to do anything. So again, how do you actually trigger this malicious behavior? That's a big challenge and all that stuff. And I kind of touched on this a second ago, but how do you counter sophisticated "am I being monitored" detection? There's another paper that came out recently, and it basically showed a step-by-step. Here's how you detect that you're running within an emulator, and if you're running within an emulator, just don't do anything. So it's fairly trivial for malware to just simply say, okay, I'm just not going to do anything. So kind of an issue. The other thing is realistic user input. If you're trying to automate this, how do you get realistic user input? And then how do you I'm going to skip over a couple of these things, but how do you efficiently capture all interaction with the system? So that's another challenge. Like, how do you actually capture what's happening? So, and then finally, once you have all this flood of data, what do you do with it? How do you analyze it? So, if you were to Google, Android system architecture, and you go to Wikipedia, this is the image you would see. So this is just basically. This is actually getting somewhat dated now, but it's still so relevant. If you look at this, if you look up here at the top tier here, these are the different applications. So if you write an application on Android, it's going to be up in this higher tier. And if you want to do anything interesting with it, if you want to make a phone call or you want to use a camera or whatever, you need to interact with the application framework, which in turn interacts with the lower libraries and then ultimately all on top of the Linux kernel. So if we want to record all this stuff, somehow we need to get in the middle of this stuff, right? So we need to figure out, like, what is this phone doing? Well, what is this application? The phone being an application, right? So what exactly is it doing? So that's the idea here. So the idea here of just trying to set up the idea behind this is, so we made the observation that in order for any malicious behavior to occur, like if you want to do any sort of network connection or write something to a file or something like that, you basically have to use a system call, right? So it's kind of common sense, but that's how you got to do it. So the idea is if we were to somehow be able to record network, file, and binder, which I'll talk about this more in detail in a second, but also process related system calls. And so if we were able to record all this stuff, theoretically we should be able to really see what's happening with all the full interaction that this application is doing. And so the idea is we want to be able to observe and compare the application behavior within the multiple environments, instrumented platforms. And then we also want to have some way of semi-automating the UI interaction so that you're not actually having to click through this stuff to the application manually. And then finally we have an and automated report from the post-processing of the raw logs. So some of the system call groups that we look at are, nothing too exciting here, but just, all the network-related system calls. We want to basically hook these, examine what's happening. So, with socket, connect, send, and receive. Connect is obviously useful because you can tell which IP addresses this application is actually connected to. Now, obviously, you can get a lot of this stuff with something like TCP dump or PCAP analysis. But what you can't, or at least is very difficult to do, is actually figure out which traffic flows are assigned to that specific application, right? So you can say, yeah, something on this phone was connecting to this IP address over here and doing stuff. But trying to actually bridge that gap there, that's the whole idea with this. And the file is useful because we can track all the file interactions that the application is doing. Every file that opens, reads, and writes, and so forth. And the binder, I'll describe this more in a second, but that does the, we basically hook the ioctl system call. And by doing that, we can actually, this is very interesting, we actually track all the interactions between the application and all the Android services. And then process, we also look like every time it runs exec, like let's say that some malware that we've seen, well, some of the older ones, will actually include a ARM binary, and so it'll actually try to execute that. And sometimes with the whole concept of rooted phones, you'll have the SU binary on there. So you'll see exec SU, and it's trying to, who knows what it's trying to do, right? So zooming in on the Android system interaction, the way this works is, so for the binder module, turns out that every time that the application wants to interact, so again up here, you guys can see that, yeah, okay. So anytime the application wants to interact with the framework, the system services, it actually goes through through the kernel, believe it or not. So what it's doing is it ultimately, through a long path, it actually goes through here, the binder driver, and then from there it's able to interact with the different applications. So by sitting at that layer, we can actually get a whole lot of very useful information. So some examples that we can do, we can actually track sensitive transactions. Every time it tries to retrieve the IMEI or the phone number, something like that, we can actually track all that information. Also, interestingly enough, we can, anytime we get SMS messages sent out, we can actually sent or received, we can actually retrieve that as well. So now that we have this kind of this concept of how to do it, how did we actually build it? How did we design this? Okay, so the first idea here is more more intuition. Is that so the first one up here, this guy here is the emulator, right? So the emulator is typically something based off of QEMU, if you guys are familiar with that. So this is obviously a very well-known virtualization software out there, and it's very easy to scale, right? You can just have a server out there and have a whole bunch of instances, and it's very easy to scale. There's the problem with that, though. Although it's easy, it's also very easy to detect, unfortunately. So even though this seems like the easiest solution, it's not the perfect solution. So what we did is we actually used a combination of all three of these. So the other approach here, the second one here, the ARC, this is kind of interesting. In the last year, really, we're seeing a lot more of these 64-bit ARM server environments. So with these things, you can actually have it's very similar to like an x86 based platform where you've got full hardware virtualization capabilities, and it's actually got like a lot of memory you can throw at it. So you can have like 128 gigs of memory or something like that. So with that, you can have full hardware virtualization. So you can actually have a virtual Android instance, and it's also it's much more difficult to detect, although it's still possible. And then finally, obviously the phone. This is a Nexus 5, I believe. And so with this one is actually the best environment because it's an actual phone. It's very easy to instrument it. The problem with that, though, is it doesn't scale very well, right? So if you're trying to go to the level of you've got 1 million applications, you're trying to, it's very difficult to visualize a data center with 1 million phones just stacked up in there, right? I mean, it's just doesn't work too well. So okay, so once we have all this stuff set up, the big picture here is ultimately we upload an APK. An APK is basically just an application. It's a zip file essentially. We would take that, do some initial static analysis on the application. We would then drive the user input, and then then we basically do that on each one of these platforms. So we would do like on the previous slide, we would have the ARM server, the modified emulator, and also the physical phone. And then once we've done that, we basically take all the results, combine them together, and then we can generate the final report. So jumping to the implementation part, what we did, so we decided on the phone, in the ARM server, we decided to go with a kernel module where we just basically hook all the system calls, which is nothing new. I mean, this has been done for a while, but we decided to do it on an actual Android phone. And on the emulator, we used a QEMU plugin, so we're really doing so essentially we're using virtual machine introspection techniques. So by doing all these things, that's the whole idea of how it works. So the way that worked, we can jump in here. This is how we actually implement it on the kernel module part. So if you look at the Linux kernel today, you'd see the system call table, which is interestingly, it's not an exported symbol. So if you guys have done any kernel program, has anyone here done any kernel program before? Okay, a couple people. Okay, so yeah, so if you're doing some kernel programming, basically you've got an issue where, for security reasons, they've made it so certain symbols are not exported. So if they're not exported, it's kind of tricky. So anyway, it took a little bit of work, but we were able to finally find that the system call table, and then from there we were able to redirect it. Now the way you read this is basically the system call table has the addresses of these various functions out here, like for example sysclose or sysopen. So that would actually store the address there. So all we do is we just basically figure out what that is and replace that with this one right here, and then what we can do, we can actually process that before the actual call is actually run, and then once it's done, then we simply send the response back. So you can't really tell that it's running. Okay, so that's the kernel module idea. And the next one here is the VMI based architecture. So this is the part that's run on the emulator. So the way this works is you've got the way to read this is so up here a user process somehow executes a system call, right? So as soon as it executes a system call, what happens is that it at some point through the flow, it generates a software interrupt. Okay, so a software interrupt is we can then pick this thing up within our plugin, and then we can actually process the actual system call basically, and then once we're done processing it, we then pass it off to the kernel. So then the kernel processes it normally, and then we get the return from it, and then it goes back up here. So this is nice in that we really don't have to modify anything in user space or in the kernel space. So it actually gives you a little bit higher assurance level. So moving on to the analysis part. So basically we have several different approaches here. So the first approach is the static analysis. this is where we package and we basically parse an APK. We look at what's called the manifest. By the way, have you guys ever done any Android app development here? Is anybody, someone familiar with this? Okay, good. I just want to see if you guys understand what I'm talking about here. All right, so yeah, so basically, if you know what the manifest is, that's where you set all the different permissions requested and all, and you also say, okay, these are the services that are starting and stuff like that. So you declare all that within the manifest. So the idea is we just kind of do some very lightweight parsing of that. We kind of say, okay, these are the different applications, and we also look to see if there's any native libraries out there. So there's another interesting gap with mobile in the mobile space right now, where it turns out that most, at least from the last several years, most of the malware that we've seen, all the ones that really do anything particularly malicious, it's all done within native libraries. So we don't ever see anything like in the Java level, oh yeah, let's do something really malicious. It's typically done within a native library. So we've done some work on this to try to look at this a little bit. And so the way that we do that right now, it's very rudimentary, but we actually track all the possible system calls that could be done on this particular library. Then once we know that total list, we can then use that to help with the actual analysis later. And then the next part is obviously the Android API call inspection. This is really more the binder inspection. Okay, so we can basically track data leaks, look at privacy issues, and some of the things we can look at is from the previous slide. This kind of explains this a little bit, but we can look at every time an application tries to access the camera, retrieve IMEI or contacts or whatever. We can actually track all that information. Also SMS traffic. Now for the network part, we I think I touched on this a little bit briefly, but we also use like an SSL MITM or man-in-the-middle proxy to actually record all the traffic. So a lot of times you'll see that traffic will actually be encrypted over SSL, so you can't really. So if you're running something like TCP dump, you're not going to be able to capture that. So we just use that to help record some of the data, and then we also utilize tools where we can actually record all the actual data that was transmitted to see if there's any data leakage. So the other thing that we look at is some file system stuff. This is just basically parsing all the logs that were previously generated. So we'll look at the file system to see what sort of files were opened, what sort of files were read and written to, and so forth. And the process one, we were looking at some malware from like 2012, I think. It was, and this is one that was called Rage Against the Cage. I don't know if you guys are familiar with that one. It was kind of this famous one that came out. But basically, it was running a fork bomb, is what it was doing. So what that means, yeah, I see a couple people nodding their heads. Basically, what that means is that you just run fork over and over and over again, and then it finally exhausts the system, and it from that you're able to get a privilege escalation and then do all kinds of nasty stuff. So we added that in there as well to to kind of track that kind of stuff. So it turns out though that we have that in there, and the other option is the automated screenshot capability. So anytime that we find anything, we can take a screenshot of that, which is useful in the final report that we generate. Okay. So just to get a little bit more detail on the metrics that we're currently looking at, we can anytime that an application attempts to read an SMS message, or retrieve a phone number, get the SIM card serial number, and so on, or take a picture. Anytime it basically tries to get any of this stuff, it will basically log all that stuff, so we can see what's happening. So the next slide here just kind of talk about the VAMDA workflow. So the way this is work is, so first an application is uploaded to the VAMDA platform, and we basically analyze the application with the emulator environment using the actual VMI approach that we talked about earlier. And we find that this is the cheapest to deploy. So we want to be able to. This is easy to scale out. We can have have as many of these as we want. We can basically. This is useful for the less sophisticated malware out there. So anything that's doing any advanced malware capabilities, this is the best approach. And then we then analyze the applications on these other platforms, and then we can basically analyze and then compare the results, and then finally generate the report. And so this next slide here is an actual screenshot, if I can get this to work, of an application of a malware sample that we were actually looked at. So this shows you. This is kind of what we do with the on the emulator, modified emulator, and this is going to show you how it interacts. Just to let you know, this actually takes a long time to analyze an application. It usually takes about 45 minutes to an hour, just for each instance. So it takes a long time. So the video here I'm going to show you, I'm not going to bore you with a 45-minute video here. Is actually it's sped up I think by 8 to 10 times. But even then, it's still kind of tedious. You're kind of like, all right. So I'll try to walk us through it. Okay, you guys see that? Okay, all right. So here it is. It's starting it up. This is the semi-automated UI automation script that we have. What it's doing right now is it's actually installing the application, our application. Which, and again, this is 8 times speed up, so it just takes a long time to do it. But all right, so here it is. They actually installed the application, and this malware here is called Locker, and basically it's really not that sophisticated. But what it tries to do is it installs. Let me pause that for a second so we can see what's happening. So what it does is basically installs itself, and it tries to it basically keeps itself running in the front. So if you press any like the home button or something like that, nothing will work because it just always thinks that's in the front. So it doesn't really actually do anything really malicious. It just always runs in the front. So you get this pop up and it says, to unlock your device, send us $300. Okay, so that's they're trying to get this information here. So our system really just kind of goes through this in an automated fashion. Obviously, if someone wanted to go through here and actually do it automatically, or actually manual intervention, you could do that as well. But it just kind of shows you how it works. So it's interesting to just enter $300, and then once you add that $300, I guess you get it generates a special code, and then by doing that, it will actually send an email address. I'm going to show you a screenshot here in a second. But it's going to go. It goes through here, and so our UI automation is not perfect. It works, but it's not really. It could use a lot more sophistication. Okay, so it's just going to go through here, and then eventually it's going to work its way down and hit the unlock device. So I'm just going to skip ahead a little bit. Okay. All right, so by doing that, what we were able to, we looked at the logs here, and this is what we found out. So it turns out that it's actually connecting to an IP address over in the Ukraine. And what it's doing, we found out that it's this is actual message that it sent out. So in this case, it retrieved the IMEI information. In this case, this was on the emulator, so it wasn't really that interesting. But if it was running on a real phone, this is what you would see. Also grabbed what's called the app key. So it grabbed all that information and it connected to this server in the Ukraine, and that's what it's doing. So we also looked at. I mentioned earlier with the application running in the foreground all the time, and you're trying to stop it, you just couldn't do it. Well, it turns out that by analyzing the binder activity, this is what we were able to see. So there's this so it looks like it's got some kind of a for loop running. You just constantly moves tasks to the front. During that time, 281,000 times. So it's just constantly doing that. So that's really all they're doing. And in this case, it's really not that interesting, but it just kind of shows you the capabilities of what we can do. All right. This is actually going a lot faster than I was planning. But this is where we're at so far with this project. We've been working on it for about 1.5 years so far, and we've got some. I think we've got a really good start. So some of the things that we want to work on going forward is we want to look at some advanced pattern recognition. So we want to look at so we've got a sequence of discrete events that we can observe, and we want to be able to say, okay, can we actually make some high-level events out of this? So that's a big thing that we're looking at here for the next year or so. And then we just want to analyze all this stuff to see what we can find, find some additional information. We also want to work at some advanced static analysis as well. And the last category I think is kind of interesting. It's a little bit vague, but it's just advanced analytics. I mean, so we've got all kinds of data here, and we're looking at some advanced ways of really making sense of all this stuff. So that's currently what we're working on. And so what I'd like to do at this point is just kind of open it up for questions. If you guys have any questions over what we've been talking about. Yeah.
How easy is it to detect?
Turn your mic on.
I'm trying. It's not. There it is. How easy is it to detect that it's in an emulator? Like, is it just a couple of calls, or I mean, is it more complicated than that?
So right. So there's a paper out there that you might want to look up. It's called "Rage Against a Virtual Machine." Yeah, it's an interesting paper. So if you look through that, it's actually fairly straightforward to detect, especially if you're running something like QEMU that's doing ARM emulation. It's fairly simple, fairly straightforward. But yeah, that's a good question. All right, any other questions? Okay, well, I guess we'll just go ahead and finish early. All right, thank you.